morning to all of you. Today we will learn about the image restoration in image processing. Myself Jaishree Jain, assistant professor in computer science and engineering department. So we will learn how to restore the image in its original format via this lecture. So what is image restoration? Image restoration is main objective is to improve the condition, improve the quality of the digital image while we transforming the image over the network. Then there are some distortions and some noise can be added into the images. So when receiver will receive the image can be distorted. So at the receiver end, there is a requirement that the image can be restored in its original form. So actually the uh, reason for degradation are like motion can be one factor that image is going to move from one position to one location to other location, and improper focusing of camera during the capturing of the image means when we capture any image through our camera, the camera can be move or so image can be improper. So it is one of the reason. And noise, there are some channel noise or environmental noise when we transform image from through the channel from one end to other end, then image can be distorted through the due to the noise. So these are all the reasons why image quality got degraded. So while restoring the image, we have to improve the quality of the image so that this degradation can be removed and image can be restored into its original form. So this is one example of degraded image. So we can say firstly we have input as a degraded image is as input, and after applying some kind of filter we can improve this degraded image and restore the image into its original form. So this is the main process how restoration will work. So we have to actually enhance the image quality by applying some filter so that we can remove the noise from the degraded image. So main objective is that, and this is the model of restoration. Firstly, we have the image that is xy, that is the degraded image, and we have degradation function h. So firstly, we have to calculate the degradation function h. After that, we will apply some, here we get some noise eta xy. This is the noise function eta xy. So we assume that when we transform the image from one end to other end, some environmental or some channel noise will get added into the image. So obviously some noise will also get added into this degradation function, and we will get the image that is called gxy. So this is the degraded image, and then we apply some kind of restoration filters here, and after applying some kind of filter we can restore the image that is f dash xy, f cap xy. So this is a, we can say this is a combination of two model. Degradation model is here where we calculate the degradation function and noise effect, and then we are going to restore the image into its original form. So this is process is called as the image restoration model. So what is the explanation of this diagram? I already told that we have the degraded image and we have to add some noise. Actually, we all know some kind of noise will get inserted into the image, and our objective is to restore the image into the original form. So this is the implementation or restoration of the image. So this is the formula how we calculate, we can find out the value of gxy, as we have seen in the previous model that we have a degradation function hxy, and after this is a convolution function, means XOR convolution function. So we have to apply this convolution function with this original image. So we will get the degraded image plus eta xy is the noise model. So we this all will we will add this value and we will get the value of gxy. Next is, therefore, in the frequency domain, this is the value of the gxy. There are two domain, as we all know. In images we have two domain, spatial domain and frequency domain. In spatial domain we will work directly on the pixel value, but in frequency domain we convert or arrange the image in the form of frequency. So there are certain technique, how can we convert from spatial domain into the frequency domain? Like we can apply the DFT, discrete Fourier transform, and DWT, discrete wavelet transform. So I want to work in the form of wavelength, so I will use a model that is DWT. And in frequency, in case of frequency, I will convert the original image by applying the DFT, discrete Fourier transform, into the frequency domain. So when we calculate the degradation function value in the frequency domain, we use the capital GUV. This symbol will convert into this form, and this small h will convert it into capital HUV, and fxy will convert it into FUV. And noise function is eta function, that is NUV. So these all value will convert it into the frequency domain, and we can calculate the degradation function. Mathematical modeling, if you have the mathematical model, means how can we calculate this function HUV? So there is some mathematical model, so we have to apply here. Means this HUV can be calculated via this function e raised to power minus 2k u square plus v square upon of the power 5 by 6. So this is the formula, this is a mathematical model. How can we calculate the nature of turbulence? Means this HUY is a, we can say this is a turbulence function. So we have to calculate this by applying this formula, where u and v is the coordinate, means x and y position, and this k is the value of intensity or frequency of that pixel. So now next is noise model. So we have to study what are the different kind of noise. So how can we say which kind of noise got inserted into the image? So we have to study different noise model, and we have to apply different noise onto the degradation function to calculate the degradation image. So the principal source of noise of digital images arises during the image acquisition and transmission. So when we capture any image via the sensors or via the digital camera, so the image got also involves some kind of noise. If the camera position got distorted, or sensor will only move in one direction, or sunlight is very low, then the image quality can be degraded. So the noise will get inserted. Acquiring images with camera and light levels are major factor that affect the quality of the image. So images are corrupted, and that corrupted image is going to be sent over the channel, and receiver will get the noisy image. So we have to remove these all kind of noises. So we can divide this noise model into the 5 noise model here. First noise model is Gaussian noise, then relay noise here, and gamma noise, exponential noise, and impulse noise. These are all the noises that got inserted. It depends which kind of noise we can say will going to added into the image. If this is the atmospheric noise, then we can say there is a Gaussian noise. If there is a channel noise, then we can say there is a relay noise. So depending on the condition, different kind of noise got inserted into the image. So this is already we have studied this degradation function. GXY will we can get the value of GXY with the help of FXY plus eta XY. This noise will get inserted into this image. So this is the degraded image, and noise will got added, then we will get the value of GXY. This is the kind of spatial domain, and in case of this is a spatial domain, and this is the frequency domain. So we have to calculate in both domain, we have to calculate the value of the noise. So first is Gaussian noise. So we all know Gaussian noise is a probability. We have to calculate the probability density function of the Gaussian random variable Z. So this is a variable Z, that is the Gaussian value of any pixel. Then we have to calculate the value of probability density function is equal to 1 upon root 2 pi sigma e raised to power z minus z bar square upon 2 sigma square. So this value is, we can say, where z bar is the mean value of the z, and sigma is the standard deviation, sigma square is the variance. So here we apply some mathematical statistic terms like z variance and like standard deviation. So by applying or calculating these value, we can get the value of Gaussian noise, and this is the curve of the Gaussian noise. We can see here, this is the Gaussian noise curve. Here we get the value, if value of z is like here something, the value of 0, then 1. Pixel value can be anything. If it is a grayscale image, then pixel value lie between 0 to 255. And if it is black and white, means 0 and 1. And if it is color image, then in case of color image, we have 3 pixel RGB, red, green and blue. Like and the range of red color is 0 to 255, range of green color is 0 to 255. So here we have scale, so value can be lie from 0 to 255 here, and the curve is going to in this form, like this is a Gaussian curve, and in the peak, on the peak we get value that is 1 upon root 2 pi sigma. So this is, we can say Gaussian noise is the random distribution of the noise. So here we have less noise distribution, and after that the value of pixel get rise and noise will also get rise. Here we'll get maximum noise, and then noise will get degraded. So this is called as a Gaussian noise model. Next is, so the Gaussian noise arises in an image due to the factors such as electronic circuit noise. So when we using the device, like any electron image is going to pass to any electronic circuit, then this noise will get inserted. And sensor noise due to poor illumination. If we have acquiring the image through the sensor, then if the light source is very poor, then image will get dark and noise, Gaussian noise will get inserted here. The image is acquired by image scanners. So if I have used the source, that is image scanner, like we scan from our mobile phones, and there are certain scanners we use to scan the image, then this Gaussian noise can be inserted. So this is a big phenomena, how Gaussian noise can be inserted into the image. Fine. Next is relay noise. Relay noise is, this is the formula, how can we calculate the relay noise. P of z equal to 2 upon b z minus a e raised to power z minus a square upon b. So where z is the original value of the pixel, like in spatial domain we have value 0 to 255, and there are two variables a and b. So we have taken here two variables that they are the constant. If the value of z is greater than a, then this formula will applicable, and if the value of z is less than a, then the probability of this value is noise is 0. So here we can say this is the value of a. Here we have threshold a. So as we increase from the a, here the value of noise is 0, and if z is less than a, so there is no noise, and when is z is greater than equal to a, then the value, when we put this value into this formula, then the noise will get increased, and at maximum peak point the value of noise will be 0.607 square root 2 upon b. So the mean and variance are given by, if we calculate z bar, then the mean is a plus root pi b divided by 4, and variance is b 4 minus pi divided by 4. So a and b are here certain constant we can take here, and we can calculate the value of relay noise here. So we can say relay noise PDF is helpful in characterizing the noise phenomena in range imaging. For example, X-ray and ultraviolet imaging, and which depend upon the frequency of the light. So this kind of noise inserted into the image when we are going to capture the image in this range, like X-ray. Through X-ray we are capturing the image, or through ultraviolet imaging we are going to capturing the image. So when we are capturing in this range, then there will be insertion of relay noise. Next is Erdlang noise or gamma noise. This is a formula. How can we calculate the Erdlang noise? Here we have same variable a and b. The formula will get changed, a raised to power b, z raised to power b minus 1 upon factorial b minus 1 e raised to power minus a z, if z is greater than equal to 0, and if it is less than 0, the value will be 0. and this is a mean B upon A, and this is a variance B upon A square. And here this is a graph of this gamma noise. We can say this gamma noise is getting skewed towards the left. Here the maximum value, here we get K, and this value is B minus 1 divided by A. So this is the value of noise. This is the value of this point. We are getting the value B minus A divided by A, and this point is K, where K equal to A factorial B minus 1 raised to power B minus 1 upon B minus 1 factorial and E raised to power minus B minus A. So this is the formula. How can we calculate the value of gamma noise? So gamma noise points in laser imaging, where we have laser scan, laser surgery images. So we have involvement of the gamma noise. Next is exponential noise. Exponential noise means, its name suggests, exponential means noise will getting rise or exponentially decrease or exponentially increase. So here we are getting the graph. The noise is going to exponentially decrease from, if z is greater than 0, the value of noise is e raised to power minus az, and if it is less than 0, the value is 0. Mean is 1 upon a, variance is 1 upon a square. So exponential PDF is special case of long PDF with b equal to 1. When we have the value of b equal to 1, then only a is the dependent variable. So we use this noise involved in laser imaging. Fine. So this is also in laser imaging when b equal to 1. Next is salt and pepper noise or impulse noise. It's very important. So basically this is caused, actually this noise is caused due to the environmental or air pressure or all that reason. So here we get the value of the noise, that is PA and PB, when z equal to A and z equal to B. So what is the value of PA and PB? This is a question mark. When at the value at this position A, we get the value of noise PA, and the position of B, impulse noise value of P is P of B. So when, if B is greater than A, then intensity B will appear as a light dot. Means if variable value of B is greater than A, then we get the light dots on the images, but and A appears as a dark dot. Means A is getting dark and B dots are light. If either PA or PB is 0, means this value is getting 0 here, then the noise is called as a unipolar. Means there is no noise, unipolar noise will be there. Both dots are going to be same. If neither probability is 0, and especially if they are approximately equal, if PA and PB is equal, then impulse noise value will resemble as a salt and pepper granules randomly. Means PA and PB is equal kind of dot will be there will be light dot, and in equal manner there will be the dark dot. They are distributed over the images. For this reason, bipolar impulse noise is called as a salt and pepper noise. So the name suggests like salt and pepper, like we have a salt in the form of dots. So we, in the images, when this kind of noise get inserted, we got the some kind of dots in the images, that is called as a salt and pepper dots. Salt means light dot and pepper means dark dot. Fine. So these all are the noise model and their PDF. So we have studied 5 or 6 different kind of noise, like Gaussian noise, relay noise, long and gamma noise, exponential, uniform and impulse. And impulse noise is also called as a salt and pepper noise when P equal to PV. So this is a curve for Gaussian noise, this is relay noise, this is long noise, and this is exponential noise. This is uniform noise, is one kind of noise where we get the noise getting increase here at the maximum point, it get constant, and at B point it get decrease. And this is the impulse noise. So these all are called as a noise models. And this is the effect of noise model. If this is the original image, and if we are getting noisy or degraded image, then Actually, this is a histogram. This is a histogram of the original image. If I plot the histogram of this image, then there are three different levels: white, gray, and black. So we get different level like white, gray, and black. And if this images get degraded, like if this is in the form of this model, so we have this white color, this is a degraded white color, this is a degraded gray color, this is a degraded black color. So we will get some distortions here. So this is a distortion, this is one distortion, this peak is telling us that there is some distortion. So this is the case of Gaussian noise, this is the example of Rayleigh noise, and this is the example of gamma noise. Here we have the example of exponential noise and salt and pepper noise like this. This is called as salt and pepper noise. So these are all the histograms of noise models. Then we have to apply for noise removal, we have to apply some restoration filter method. So what are these filter? Like first filter is the mean filter. Mean filter in which we apply arithmetic mean filter, geometric mean filter, and harmonic mean filter. So these are all the filter. Contra harmonic mean filter. Mean means averaging. So we have to apply some kind of average or so there are different mean filter: arithmetic, geometric, harmonic, fine, contra harmonic. Next is order statistic filter, where we apply some static parameter like median filter, max and min filter, midpoint, or alpha trim filter. And last is adaptive filter. In adaptive filter, we have adaptive local noise reduction filter and adaptive method filter. So there are three category of filters in which we have different categories of filter. So these filter are going to apply to remove the noise in the spatial domain. So first is arithmetic mean filter. As the name suggests, arithmetic mean means this is like an averaging filter. So if we have the degraded image DST, then we sum all the pixel will get added here and divide by mn, where m and n is the size of the image. So m is the total number of xx pixel on the x-axis value. This is the dimension, how much dimension of the image is there, because image is in the form of two-dimensional. So we get value of m and n. Like the image can be 32 by 32, so the value of m and n will get 32 and 32. So this is the arithmetic mean filter. So we can simply apply this filter for smoothing of the images. So if I want to achieve the smoothness in the image, so I will apply this kind of filter. Next is geometric mean filter. So this is the opposite of arithmetic mean filter. Here we will get the product. This is the projection, means we have to multiply all the pixels of degraded image and its power of 1 by mn. So this is the exponential power will apply here. And this kind of filter actually achieve the smoothing and comparable to the arithmetic mean filter, but it preserves more detail. Means this filter will also achieve the smoothing in the image, but it also preserve the detail. More detail means clarity will be there, so more detailed image will be achieved. So here this is example of X-ray image. We have X-ray image here, and these are corrupted image. This is a noisy image. Then we apply the filter. So this is the result of arithmetic mean filter, and this is the result of geometric mean filter. So here we can see the detail, like geometric mean filter will clarify the more detail in the images. Next is harmonic mean filter. So this is a formula for calculating the filter of that is harmonic mean filter. The formula is mn divided by 1 upon summation st belongs to xy g of st. So this is the value of, here we have the degraded image. We will get the sum of reciprocal values of the degraded image, and we have to divide mn to this value. So this harmonic mean filter works for salt and pepper noise and other type of noise like Gaussian noise. So if we want to remove this kind of noise, we can apply the harmonic mean filter here. Next is the contra harmonic mean filter. In contra harmonic mean filter, we have just apply one parameter, that is q, where q is the order of the filter. So this filter is well suited for reducing the effect of salt and pepper noise. So for positive value of Q, eliminate the pepper noise. Q is a constant. If we are taking positive value of Q, it will eliminate the pepper noise, and for negative value of Q, it will eliminate the salt noise. So this filter cannot be reduced both simultaneously. Either we can take one value of Q, it can be positive or it can be negative. So this control harmonic mean filter reduces to the arithmetic mean filter when Q equal to 0. So, and harmonic mean filter if Q equal to -1. So these kind of all filter, these all are the mean filter we can apply to reduce the different kind of noise from the images. So thank you so much. Next filter will be studied into the next lecture.